Hi friends, sorry I'm not there today at home. I actually had a meeting all day today. Plus I'm not feeling well anyway, so at least you get my lovely voice and we'll continue on with our notes to begin with. Please follow along with me. Afterwards you'll have a chance to grab out a Chromebook. Oops, sorry, there goes the bell. Grab a Chromebook, and if you need to fill in any of our notes from how to use quadratic formula from up above, some of our examples, they are all right there for you, filled out on the classroom from last Friday, so you can grab those notes. We also have solutions to quadratic formula practice up at the front board, so check your progress on that handout and that worksheet. Just make sure you return those solutions up to the front so others can do the same thing. Today we just are going to look at some real-world connections. Why do we even care about these quadratics? What kinds of answers can we find using it? And we'll see that there are lots of ways we can solve these, very much like solving rational equations and rational inequalities. So we're going to have multiple ways we can go about solving these things. When we have an equation, I want to put this note here that it's going to be just like solving rationals. This is what we were doing last chapter. And so there are some ways we can go about doing this. We can solve it using algebra. We can solve it by graphing. Sometimes we can solve it by factoring. So there are many ways to go about it. I'm going to show you each time how we would set it up and solve it algebraically, and also how we can check it by graphing to make sure that we've got it right. And then afterwards there'll be a practice that you can check your understanding with this to see if you've got it. Alright, the function y equals negative 16x squared plus 270 models the height y in feet of a heavy object x seconds after it is dropped from the top of a building that is 270 feet tall. If you want a visual of this, we have our tall building here. It is 270 feet, and we're dropping something from that top of that building. Now when we drop something, it tends not to just fall straight down, it actually falls in an arc like this. So this is where we're getting kind of that quadratic shape. Remember, quadratics are either U-shaped or upside down U-shaped. This one happens to be an upside down U shape. And we want to find how long does it take the object to hit the ground. That means it's going to hit here, if we kind of think of it like this, on a coordinate grid. We have our starting point at our time of 0. As it falls down, it's going to lose height, and eventually it will have a height of 0 at a certain time. And so we want to figure out how long this time is from 0 to when it lands, so that we know how long it takes that object to hit the ground, to have a height that was 270 feet and now has fallen down to 0. This means, if this is the function that models this arc, I want to find out when does that function equal 0. So to solve it first algebraically, we could actually do this a couple different ways. Maybe we want to go right to quadratic formula. We have an a. There's no b value in here because there's no x term, so b equals 0. And we have a c term of 270. So, thinking about our lovely quadratic formula song, let's sing it and place our values in place as we go. X equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. And so I put all of those values in as I went. Now I need to start seeing what kind of information this simplifies to. So I need to know, what does negative 4 times negative 16 times 270 equals 17,280. 0 plus or minus the square root, 17,280 over 2 times negative 16. In my book, that's negative 32. And since I'm talking about something about time, it's okay if I'm just using a decimal approximation. When we start getting these real-world connections, some of them have to be exact, but this one is something that we can approximate. We want to know about how many seconds it takes. So I'm going to do this actual math in my calculator and find out when we do this. Let's see, the square root of 17,280 equals 131.45. Now there's a plus minus in front here, so I'm going to carry that with me. Remember, a square root could be a positive or a negative number. Now I'm not adding it to anything because there's a 0 out front. So I have 131.45, and I'm going to divide that by a negative 32. So to take this number now that I have and divide it exactly by 32, I'm going to do it right from this decimal that is already here in my calculator and divide it by a negative 32. This way I get at least all of these decimal points, even if I didn't write them all down on my paper. And I find that I have a positive or negative 4.108-ish seconds. When I think about this in reality, because we always have to keep ourselves in reality, time will never go backwards. So it doesn't make sense that I would have a negative 4.11 seconds. It makes sense that I would have a positive. It would take 4.11 seconds for it to hit the ground. Now, if you wanted to solve this on your calculator, we solved it algebraically using the quadratic formula. We could also solve it by graphing. So I always want to show you that example as well. I'll use one of your calculators so you can see what it looks like on your style. Going back to my original equation, it's already equal to 0. That's going to be important. Remember, we did that every time with our rationals unit, as we set it equal to 0 first. We're going to do that same practice here. This one's already equal to 0. So by typing in my equation, I'm going to start with the zoom 6, but I guarantee you I'm not going to be able to see the top of the graph because it's 270 feet up and my calculator starts everything at 10. So it's going way up off my screen, but I do see the zeros where it is going to hit the ground, right here and right here. Now again, this is a negative time and this is a positive time, so it makes sense that I find this 0. So if you do solve these by graphing, as per usual, I ask you that you'll always sketch your graph so I can see what it is you're looking for. We're looking for this 0. And so on my calculator, I would go second calculate. I'm looking for a 0. It's asking me for a left boundary. Now these coordinates tell me where my cursor is right now. It's 0 side to side and 270, so I'm way up on the top of my screen. I'm going to use my right arrow button to start getting closer down here until I hopefully see it appear. Oh, it's starting to get lower and lower. It's starting to come down where I can see it. Oh, finally, there's my cursor. I'll hit enter, and now I need to keep going to the right until I know I am past. And I already can tell I'm past because I'm down in the negatives. Somewhere between there is a 0, and it finds it at exactly the same place that I had calculated previously. So my 0 happens at 4.11-ish seconds. We'll take everything to 2 decimal places and round appropriately. Moving on, let's check our example B. A smoke jumper is a firefighter who parachutes into areas near forest fires. I had a friend of mine who wanted to be a smoke jumper for a very long time. And they do jump out of airplanes into a raging fire down below to put out those fires in remote locations. When they jump out of the plane, because the plane is moving forward, they also have a parabolic path as they jump out of the plane. The plane is moving forward, and so they have a forward motion. They already have forward momentum until they fall into gravity. They're in free fall from the time they jump out of a plane until they open up their parachute. So partway down is where they're going to open up their parachute to fall the rest of the way. That function is -16t squared plus 1400. It models the jumper's height when they start from a height of 14,000 feet. We want to know the time it takes that they are in free fall from this time they're here at 14,000 feet until they open their parachute here at 1,000 feet. So again, if we put this on a coordinate grid, we have a 0 time where they jump out of the airplane. Then they have this point in time where they open up their parachute. And then they also have another span of time where they will land on the ground. We're not interested in when they land on the ground. We want to know where they hit this 1,000 feet of elevation. So I need to know this time in between here of how long they're in free fall. I want to know, using this model, how long it takes until that model equals 1,000 feet. Thinking about how we solved it algebraically using rationals in our previous chapter. Our first step was that we pushed everything over to equal 0 first. And I'm going to use that same step here, setting it equal to 0 first. I have to do this because my quadratic formula only works when it's equal to 0. So we're still using the same strategies we talked about last week of setting it equal to 0 first. Now I have an A that equals -16. Again, I have no B value, and a C at 400. I can use my quadratic formula. Some of you may also be saying, well, hey, we only have one T value here. Could I also solve it by moving some things to the other side and dividing by -16 and then square rooting? You certainly could. So if you are a person who looked at this and said, well, hey, I could move this 14,000 over here, you could do that as well. We could have done that up here too. Solving by square roots is another way to go about solving these equations. I'm going to stick with my quadratic formula first, and I'll show you that as well. We can also look at it by graphing. So lots of ways to go through these. Whichever one works for you, find it, stick with it. Using our quadratic formula here, with an A of -16, a B of 0, and a C of 400, we sing our little song. X equals opposite B plus or minus the square root of B squared minus 4AC all over 2A. Solving that further, 4 times 16 times 400. It's a -4 times -16. times positive 400. My calculator gives me plus or minus square root of 25,600 over a negative 32. Again, I'm going to square root my answer. Look for a decimal approximation of it. Ooh, I get an exact. Plus or minus 160 over negative 32. I get a positive or negative 5. Now again, time doesn't make sense to go backwards. From here, we're not going backwards in time, we're only going forwards in time. They're going to count 5 seconds, and then they can pull their parachute. This is how they are able to do it, because watching an altimeter, the thing that would tell you what altitude you're at, while you're in free fall can be challenging. Instead, if they know that they just need to count to 5 seconds, that's a lot more realistic for them to do. If you'd like to see it solved that other way I was talking about, where we could move everything over, because we only have one variable in one place here. If we took it from right here, sorry about that. If we took it from this point right here, let's say I added the 16t squared to both sides. Having a positive 400 equals a positive 16t squared. Maybe you're thinking to yourself, well, I could solve right from there by dividing both sides by 16. And I find that equals 25 when I divide 400 by 16. And now when I square root both sides to get t by itself, I would have that positive or negative 5 seconds. There are times when we can solve, if we don't have a b term, we can move it over and solve in that way. Or again, we can always solve by using our calculator and our graph. Set it equal to 0, type it into the calculator, take a look at your graph, and we're going to see a 0 happen right here at 5 seconds. Calculating that 0, moving our left boundary and our right boundary until our 0 is in between. We can find it that way as well. Ask our teacher to pause the video if you need to, but I'm going to keep on moving forward because there are 2 more examples on the back side. A player throws a ball up and toward a wall that is 17 feet high. The height of the feet of the ball t seconds after it leaves the player's hands is modeled by this equation. And our question is, will the ball go up and over the wall? Will it reach a height of 17 feet before it comes back down? Or will it hit the wall and bounce back down to the ground? So we are looking at this parabola of what this person has shot the ball, how they have thrown the ball up towards the wall. And we want to see if its maximum height is taller than 17 feet and will go over the wall, or if their maximum height is shorter than 17 feet and then it's going to hit the wall and bounce back down. So this is a slightly different kind of way. I want to know this equation if it's going to reach a height of 17 or not. I want to know if it can equal 17. So again, we're kind of gridding this on a timeline here. We have time and we have height. And we want to know if that height can ever equal 17. All right, pushing it over, so we set it equal to 0. I'll subtract 17 from each side. I have an A, a B, and a C value. I'm ready to go to quadratic formula. I couldn't use that other algebraic way I was talking about this time, because this time I have a B value. I have t in 2 places. So I'm stuck with either algebraic using quadratic formula by factoring, which this looks like a tough one to factor. I could graph it and see. Let's do it algebraically first. Opposite b plus or minus the square root of b squared, I need 25 squared, minus 4 times a, negative 16, times c, negative 11, all over 2a. Now you're probably seeing this negative 16 show up a lot. That's because that is gravity. That's our coefficient of gravity right there. So that is scientifically accurate here on Earth. You'll see it a lot of times when we're talking about feet. It's 16 feet per second. All right, I need to start getting some math going on here. I'm going to use my calculator to see what I have underneath the radical symbol. Remember, this is called the discriminant. And when I calculate just my discriminant, I'm going to do it all at once. 25 squared minus 4 times negative 16 times negative 11. And I want to figure out what my discriminant is, the thing under the square root. And I see I have a square root of a negative number. And right there, as soon as I have a square root of a negative, you're probably already thinking, hey, this is imaginary. And since it is an imaginary number, it's not in the real world. We would have to imagine a solution here for it to be up at 17 feet. So since this is imaginary, I can actually stop right there. If it's an imaginary solution, this means it will never be in reality, and it will not ever reach 17 feet to go over the wall. So the ball will not go over the wall. It never gets to 17 feet. If I were to do this graphically, I could type in our equation. Simply substituting, well, I want to make that minus 11. Substituting x in for t, and we just know that that's our same variable. Notice I'm doing this one here that's equal to 0. And now I'm going to graph it and see what it looks like. And notice that my parabola never hits the x-axis. That's like this thing being up at the 17-foot wall right here. This is my 17-foot height, and this ball, here's the path of the ball that he threw up. It will never get that high to 17 to go over the wall. So it doesn't ever get that high. It doesn't hit the x-axis. We don't have any real solutions. Everything's imaginary. Some of you might be like, well, that's kind of strange. That seems weird. If we graphed our original one, and we put a horizontal line at 17 feet, the height of the wall, we can look at it that way too. Oh, except I'm going to need to change my window because 17 is up too high up here. Let me change my window, my Y maximum up at 20 so I can see this. So here's the path of the ball, and here's the height of the wall, I can see that it's never going to reach high enough to go over the wall. That kind of pairs up nicely right here with our picture that I drew. You can see that path of the ball and the height of the wall right here. Businesses will use these quadratic equations as well because they can model things like profits. So this gas station is modeling their profits based on the price per gallon of gas. It makes sense that the more they can charge per gallon of gas, the more gas they'll sell and the more money they might make. But if the price of gas goes too high, they'll sell fewer gallons of gas, even at that higher price, and they might not make as much profit. So their profits can do the same thing. At a very cheap price of gas, they will sell a lot of gallons. But because they have to pay for the gas, they're losing money because they have to buy it at a certain amount and they're not charging enough for it. At some point, their profit will start to go up, but if they charge too much per gallon, fewer people will buy their gas and their prices will start to go back down again. If you're in economics, you already know how this goes, where you have the price-profit relationship going on and the idea of supply and demand too. So this models their profits, and we want to know if they can ever profit $4,000 per day. So is that profit point, is it here where they can hit it at a certain couple of prices per gas? Or is that profit point of 4,000 up here and they may never ever get there? That's what we're looking to see. So we want to know if this equation of their profits will ever equal $4,000. And if so, what is the price of gas that would make that happen? Or maybe there's two prices. See, here we could have two prices of gas that would get us $4,000. Up here we might not have any. I see a pretty nifty quadratic. Graphing this would be really troublesome because look at our numbers. We're here in the thousands. So going straight to quadratic is probably a nice way to go about doing this problem. Subtract 4,000 from both sides so we get it equal to 0. It's our first step every time. Equals 0, I have an A value, a B value, and a C value. And we're going to go to our quadratic equation as we look at this. Opposite B, opposite 34,500 plus or minus the square root of 34,500 squared minus 4 times A, negative 15,000, times C, negative 20,800, all over 2 times A, negative 15,000. Whew, that's a lot of numbers going on there. A lot of numbers don't scare a calculator. They don't scare me either. Let's get this all typed in and see what we end up with. 34,500 squared minus 4 times negative 15,000 times negative 20,800. I'm just doing the discriminant. When I just do this discriminant, this is what's going to tell me right away. And sometimes we may just skip right to doing that discriminant, that b squared minus 4ac. Because it doesn't matter what that number is, it is the square root of a negative. And any square root of a negative is going to tell us that there is no real solution. There is no price that they could set for gasoline that would ever give them 4,000 daily profits from this gas station. So no price per gallon would give a $4,000 daily profit. So we're starting to see in reality there are times where we might find an answer that could work, and we might find times that it will never be possible. We can see when we're breaking reality and when we're able to uphold it. I'll post this video up to our classroom as well, so if you need to watch it again or hit pause at any point, it'll be there for you. But at this point, it'd be great for you to, first of all, check your solutions to using the quadratic formula worksheet that we picked up on Friday. Those solutions are again at the front bulletin board. Also, from the pickup station, there are some questions here that are going to have all kinds of models in the real world asking you to find these solutions. Pick one of those up, give it your very best try, and I'll see you tomorrow with the solutions. We'll see how you do.